All right. So, welcome, y'all. Online students, you're not getting to necessarily benefit this, but I'll mention it. So, I have 5x8 note cards. I've got more, y'all, as well. So, if you're like, man, the stack's getting low, I bought more. Like, there's more. But yeah, 5x8 note card. Our test is next week, Wednesday and Friday. It is on 2 days, not because I want to make you suffer. The goal of that is not because I want to, that's not the goal. The goal is actually to help you all. The alternative to giving you all, so by putting it on 2 days, I'm effectively giving you all twice the amount of time. That's the mindset here. As opposed to me giving you, if I just gave you the test in 50 minutes, the reality is I would have to make that 15 multiple choice questions and pick 1 out of 2 free response. And you may think that sounds nice, but 15 multiple choice questions, you miss one of those, you can do the math real quick, 100. That would end up being probably 80 points out of it if there's only 1 free response. Basically, it ends up being it sucks if you miss a question more so. So, it is on 2 days because I want to give you all the best opportunity to show what you know. That means giving you as much time as I can. That means splitting the grade a bit more evenly between the multiple choice and the free response. So next Wednesday is the multiple choice. On Friday is the free response. Okay? So there is a method to the madness. Trust me, it's extra work for me. I had to make twice as many. The grader will have to grade twice as many questions as if we just had the 1 free response. So it's more effort on our end, and we would not put that. I would not design it to be more effort for me unless I felt it was worth it for you all. So, if you're upset about a test on 2 days, there's a reason for it. We'll see how it goes, but I'm optimistic. The tests are effective. Like I've made the tests and sent them to get printed. Yeah.
Are we able to work on multiple choice on
No.
the second day, or we just have 1 test and then?
Unfortunately, it will be multiple choice on Wednesday and free response on Friday. The rationale being, if you saw the multiple choice, obviously you'd be able to kind of go outside, Google it. At the end of the day, the point of this test is to see at the time of the test, do you understand it? So unfortunately, I cannot let it extend the multiple choice from Wednesday to Friday because it would give, you'd ultimately be able to kind of look up the problems and figure it out that way, at which point it would be more memory than, do you understand it, Daniel? Yeah.
So I'm a little worried that looking at a problem, having to write down all the givens,
Sure.
figure out which equation, I'm going to be spending too much time on one question.
Yep.
Do you think there's...
The multiple choice questions are purposefully quick. So, take the problems from the problem set that have a bunch of parts to them. That's the free response. The free response, I'm giving you 50 minutes for 2 free response questions that ultimately have 2 parts. So really the free response are going to look more like the problem set problems. The multiple choice may look like one piece of one of those problems. And even then, the multiple choice, so I have timed myself doing it, and that's with me writing stuff down, and it's taken me about 10 to 12 minutes to do it. That's not me bragging. That's how I determine whether it takes too much time. And that's with me writing things out. That's with me writing the givens and the missing and stuff like that. So, to that end, the multiple choice, each problem, should not take you more than a couple, 2 to 3 minutes kind of thing. And that's including the time to write down stuff. And that's like on the high end. Also a good chunk, so 40% of the problems, something like that, are conceptual. Meaning you do not plug anything into your calculator. They are the clicker questions effectively that I've kind of done. So 40% of them, no math at all. I mean, you may have to see, if I double this and triple this, what happens to a variable kind of thing. But my expectation, I will know that I've done a good time. I will know whether or not I didn't give you all enough time or I gave too much. If at the end of it, most of you all are still here, that means I did a bad job. And I'll be honest, if that ends up happening, I will do some curving and then adjust the next test. Because you all are my first class teaching 2048, the reality is I've designed this thing, I've done all the tests I can, I've done all the things I can determine to make sure it's as good as possible. But ultimately this first test is also a test of me. And both a test of me in terms of how have I done preparing you all, how did I do designing this test, And if I do not do a good job, if everyone does terrible, or at least the majority, there's only one common denominator, that's me. And so therefore, I'll curve it. I will make some shifts and changes. I don't expect that to happen. If I expected that to happen, that'd be bad. I don't expect that, but just know that that's kind of a reality. But I do expect that you all should have plenty of time. We'll see. We'll see as reality sets in if that's actually what happens. But again, I tried to pick the questions, design them so that they can be done quickly. The problem set should be far harder than this test is. With the exception of, so take the problem sets, take the problems that are about, if you rated them on difficulty, 10 out of 10 is the hardest, 1 out of 10 is the easiest. The free response is going to be around a 7 or an 8 kind of difficulty. It's not going to be the hardest. It will not be the easiest. Depending on how you feel capable-wise, maybe 6 to 8 out of 10 difficulty-wise. Out of the problem set problems. So take the problems that you're like, man, this problem is brutal. I'm not going to ask the brutal ones. And also, I will have make certain I prepared you. So pro tip, look at the problem sets, look at the quizzes. If you all have been doing good on the quizzes, the hardest problem on the quizzes, maybe that's like the free response or one part of it. The middle question, everything else will kind of be similar-ish, probably a little bit more time than the test will be. Yeah. So we'll see as it comes along. The first test is always an uncertainty. There's only so much I can say. You'll know how it is when we go through it all together. But I'm optimistic, y'all. If you've been doing well on the quizzes if you've been doing the problem sets, you should do great on this. That is kind of my goal. If you've been doing well on the quizzes, and when I say doing well on the quizzes, you understand what you're doing. You're not just looking up solutions or having someone else do it for you. If you are doing the quizzes in a way that matches what the test is going to look like, then you should do well on it. Yes, obviously, if you have someone else alongside you the entire time during the quiz, or if you're constantly looking at solutions and using those to guide you through every single quiz problem, and you're relying on those, you're not going to have those during the test. So it's not a good comparison. But if when you look over those quiz questions and you can solve them yourself without needing to look at a bunch of solutions while doing it, that's when you know you're ready. That's when you know you're prepared, because that's what the test is going to be like. So, study for this test. Work together. Do all that stuff. But at the end of the day, make certain you are studying in a way that's going to match what the test looks like. Make certain you can do the problems yourself. That's always key, because at the end of the day, group work is awesome. That's to learn it. But if you want to make certain you know it, you kind of got to sit there and go through them by yourself at some point. Okay, so any other quick questions about the test or anything like that? Yeah.
Recitation questions, is that good?
I have not looked at the recitation questions when designing the test. So I'll tell you all that. 20 free response, and then it'll be pick 2 out of 3. 20 multiple choice. 20 multiple choice. So on Wednesday you'll have 20 multiple choice. And then Friday, 3 free response, pick 2. Pick 2. Okay. Yeah, way in the back.
Do we get anything for doing the third response?
If you do all 3 and the 2 you mark down, you mess up on 1, but the one you did not pick is perfect, only then will it be checked. Because the reality is, already having a grader check 400 problems, 200 students times 2, it's going to take some time. If I made them check all 3 problems, it's 600 problems, and so then you all just wouldn't get your grades back in a reasonable manner. My goal with the TA, my goal with the grader when I discussed with them is that they would get back the grading within 2 weeks of when it's done. I will have the multiple choice graded within a day or 2. And those grades will be uploaded very quickly because I can just scan them and put them in. The free response, I have to give them the time so they can do a good job with the grading. You don't want them to go through the grading super quick and not actually look at your work. So I need to make certain they have that time. So 2 weeks is kind of my goal with them. But yeah, that to quickly answer your question, if you solve all 3, you have to pick 2. Like you have to choose which 2. Otherwise, I'm just going to tell them pick 2 random ones. I'm not going to make them go through and figure out which ones you did best. I'll just say pick 2 random ones. If the third one that you did not pick is perfect, it will, as in final answer done, they can grade it in 5 seconds. Sure, that'll replace one that isn't perfect. Yeah.
Are the laws going to be on
Everything from problem set 1 is free game. Everything from problem set 1 is free game, meaning, and a reminder to you all, the stuff I'm covering today, you need to start studying that stuff like this week, unless you want to cram that Sunday through Tuesday. Like, I highly recommend the stuff I'm covering this week, because again, you get shorted a bit on time. That's just how it goes. Sorry, I can't figure out a way around this. The stuff I'm covering this week will be on the test. Very important that you all start looking through this. That's why hopefully you've kind of gotten caught up on things up to this point. Last week's stuff wasn't too bad. But this week, start studying the stuff for this week sooner than later. Do not, if you wait till Friday, that's fine. But you've literally given yourself just Saturday, Sunday, Monday, Tuesday to get through that, which may work for you. I don't know, but better to not risk it. So start the stuff from this week sooner than later. And with that, I'm going to go ahead and keep chugging on this. If you all have any more questions, come on by at the end. I'll answer them then. But yeah, let's get through this stuff. So today my goal is to do some stuff with free body diagrams. Remind you all how to do that, and talk about different types of forces. So last week we talked about Newton's laws. I told you all that Newton's laws, 3 of them, object in motion stays in motion, object at rest stays in rest. Things keep doing what they're doing. Second law, F equals ma. That is going to be our bread and butter for almost all of these problems. And then third law, for every force there's an equal and opposite. And so today we're actually going to be doing the math with these. That's really what it comes down to in defining forces. So we're going to talk about the different types of forces and how to calculate them. We're going to label those forces on a diagram and then find the net force and the net acceleration. That's what every problem basically boils down to in this. At the end, we will do a little bit of circular motion and forces, so we'll get to that. That'll be Friday, but hopefully we'll get through the main chunk of it Monday, today, and Wednesday. All right. So yeah, we need to remember free body diagrams. That means any problem, first step is you always draw a picture. There's a picture. Who cares what the problem is? That's what it looks like. And you draw your forces acting on it. We're going to talk about what those forces are today, the different types that can emerge. But yeah, we do that, then we draw some arrows. For example, force of gravity, force normal. Again, we're going to learn what these are. But that's kind of the idea. You draw some arrows. You start them from the center, you draw them outwards. At the end of the day, why do we even care about forces? It's because F net equals ma. That is the key. Like, the only reason for you to add up forces in something is to find the acceleration. The acceleration is what's actually going to happen. Remember that whole fly in the truck situation? They both experience the same force when the truck hits the fly, but the acceleration is actually what's going to happen. Like, that's the observable thing. Their velocity will change. How much will it change by? That's where it gets interesting. If I told you I applied 500 newtons to an object, that tells you I pushed it. And that's kind of it. It doesn't tell you what the object's going to do. If I told you I pushed a cart that weighs 10 kilograms with 500 newtons of force, you can calculate the acceleration. 500 divided by 10 is 50. That's a ridiculous acceleration. And you'd be like, that cart's going to go flying across the room real quick. The acceleration is what we care about. And yeah, so that's all today. All this whole week, add up forces set equal to mn. That's what it's going to boil down to. But we need to learn what the forces are, and that's kind of our first thing. Here's our list of forces we're going to talk about. Now, I say drag here. I will talk about drag. There's a problem in the problem set. I'm not going to bother with it. Promise you all it's not going to show up in the quiz or test. Drag, air resistance, I will talk about it. But honestly, on the problem set, which one is it? So if you all go to the very end, this problem here, terminal velocity, don't worry about it. Sure, if you want to solve it, go for it. But if you got to sacrifice a problem, like, I do not necessarily care about terminal velocity. It is something that we will talk about because it's just useful, but I'll do it very quickly. But I'm not going to honestly spend the time and energy on it because it's just not, there's bigger fish to fry. All right, but we will talk about the rest of these. Every single other one in here is important. Gravity, normal force, tension, spring force, friction, all of those, very important. So, all right, speaking of free body diagrams, let's go ahead and jump into a problem. So our first problem here is to draw a free body diagram of you sitting in a chair. It does not matter who you are, it does not matter your size, it does not matter what chair you're sitting in. This free body diagram will look the same for everyone. I guess you could simplify this. Maybe sitting on a stool would maybe be a bit better. But which of these is the correct free body diagram for someone sitting in a chair? Now, I did not label these arrows because I haven't quite taught you what they all are. But just think about what forces are acting, even if you don't know the names of them, what forces are acting on you and in which direction? That's what this question is asking you. Hey, there you are in all your boxy glory. What forces are acting on you? What direction? Pick the one that corresponds to that. The first one is you, and there's a force acting on you downwards. B says there's a force acting on you downwards and a force acting on you upwards, and they're equal in amount. C is that there is no forces acting on you. There's no arrows. And D is not enough information. All right, we'll go to 55 on this. It's a know it or you don't situation, no math. 5, 4, 3, 2, 1. I'll give you 2 more seconds.
It's not.
That's fine. Just shoot me an email. This would be a great type of clicker question, or like test question, conceptual question. All right, so what's acting on you? Well, here you are. All right, hopefully everyone knows gravity's pulling you down. But if you all think of Newton's second law, F net equals ma, if that was your only force, you all should be accelerating downwards. None of you are accelerating downwards. So by extension, even though we haven't labeled what this force is, even though I haven't taught you it, there must be a force pushing up on you. Otherwise, you best be falling. Not just falling, but falling faster and faster and faster. So there you go. The answer is B. In almost every single problem, you can expect gravity to exist. I am not going to be giving you all problems in space, is basically the punchline here. Because every force you all experience, every object, every kind of interaction you'll have is on Earth. So all the problems are going to kind of match that. So we're going to get into the first 2 forces. That is gravitational force, normal force, and we'll also talk about tension. The gravitational force should hopefully be the easiest one, but here it is in all its glory. Gravitational force, the force due to gravity. Any object of mass experiences it. On the surface of Earth. On the surface of Earth, this force is m times g. The derivation, I don't even know if you call that a derivation. F net equals m, so F equals ma. What acceleration do you experience due to gravity? G. There's the derivation. You just replace A with G. G is the acceleration you experience. This is always downwards. I guess if you flip yourself upside down, But in our case, we're going to assume down, that no one's looking upside down and saying, no, it's up. If you got strong feelings about this, just know, for my purposes, for this class, gravity is downwards. The Earth, we're always going to say, is below you. Now, again, this is on Earth specifically. Every problem basically I'm going to give you all is going to be on Earth. A little bit of foreshadowing is G is negative 9.8 on the surface of Earth. As you get away from Earth, that value decreases. We will learn about that eventually. But for now, you are blessed that G is negative 9.8 always in every problem. Fairly straightforward. Fg equals mg. So in any free body diagram that you all draw, you can expect to draw gravity down. It's going to happen. All right. See how we do with this? If you have a mass, you know what? I'm going to change. What is the magnitude? I'll clarify that. Remember, magnitude means absolute value. If you have a mass of about 70 kilograms, that's 70 times 2.2, a little bit above 140 pounds. Some of you this will be acting to, some won't. It doesn't really matter. Who cares? If you have that mass, what is the magnitude of the gravitational force acting on you? Is it 70 newtons, 70 kilograms, 686 newtons, or 686 kilograms? Clearly, this is one of those problems where I'm I am testing your understanding of the units. Obviously, there's 686 shows up twice, 70 shows up twice, but they have different units. Because the units matter. They matter a lot. All right, we're going to go to 110 on this because, again, it's, yeah, we'll go to 110. In 5, 4, 3, 2, 1. All right, so real straightforward. FG equals MG equals 70 times 9.8. Now again, sure, I'll put the negative here. The reality is, I think I've mentioned this to you all before. When you are solving for vectors, assign the direction based on the picture. Assign the direction based on the picture. So you could totally put negative 9.8 in here. That's fine. That's why I put magnitude. Magnitude means take the absolute value. So this does come out to 686 newtons. Newtons is for force. And again, technically negative, but I asked for the absolute value. That's what magnitude means. Okay? Yeah.
Notice on some of the problem sets, you don't say magnitude, but the gravitational force is positive.
Yeah, so what I will do in that case, one, I'm going to go back and double check that. I've tried to be more careful with that in the test. And also on the test, if I care about the sign, you will see different signs in the answers. That's also an indication. That's also a little trick with these. All of these were positive, so you kind of couldn't get, there was no gotcha moment kind of thing. But if a problem has answers that are positive and negative, yeah, then I care. If it's a free response, I just care that you're showing me the direction. If you say the force is 686 newtons but downwards, that also works. But yeah, I'll try to go through the problem sets and clarify the wording there. Yeah, there's kind of my response to that. I'll try to do a better job with those. All right, so how do we do? Very good job. Very straightforward. Very nice. All right, so I actually pulled this problem. This is actually from last week's problems. I realized it kind of snuck in there, and I realized, I should probably talk about it today, since we kind of need the stuff we talked about today to solve it. So, a body of mass, 2 kilograms, is pushed straight upwards by a 25 newtons vertical force. What is its acceleration? First step. Draw a picture, free body diagram. I want you all to spend 10 seconds thinking about what arrows should I draw on this thing. It says it is pushed upwards with a force of 25 newtons. So there is a force upwards. But remember, you can assume every problem I give you is located on Earth. I will tell you if it's not on Earth, but it's going to be on Earth. There is a force due to gravity of m times g. Okay? And this problem says, what is its acceleration? So, givens. We have, it says it's pushed upwards. What do you want to label that as? You can decide. What I use with my high school students, I call it applied force, a push or a pull. If it literally says someone's pushing something, call it whatever you want. I call it applied. It's just an applied force by something. So we'll just call it FA, F applied. But you could call it F1. It doesn't really matter here. FG is going to be, well, okay, let's do M. M equals 2 kilograms. You know what? As a given, we know we're going to have to solve for it. Let's just do it now. Fg equals m times g. So 2 times 9.8 now. Notice I'm choosing to put the positive 9.8 here. I'll explain why. You want to put the negative, go for it. That's perfectly fine. I'm going to go ahead and tell you all, based on whatever decision you make, what you need to be careful of as we solve this problem. But for now, I'm going to put it as positive. I'll explain why in a second. If you put it as negative, that's also fine. We're solving for the acceleration. If you ever see a force problem and it says find the acceleration, your mind should immediately go to Newton's second law. Anytime you all have a problem involving forces and it says acceleration, your mind should immediately say, I'm going to have to do this at some point. F net equals ma. F net. That net is critical. You have to know that it's the net force, not just any of the forces. All the forces together contribute to the acceleration. Easy way to prove, you got a desk. One person's pushing one way, one person's pushing the other way. You have to attribute both people and what they're doing. Get that net force of both of them together. And when I say F net, that means add up the forces. And when I say add up forces, that's adding vectors. That means X and Y components. This problem, we are fortunate. It is only in the Y component. But we will quickly see that there's forces, there'll be an X and Y many times. So, we're blessed here. If we kind of write this out, F net, so the other equation we know, whenever we say F net, okay, we should also write what F net is. F net is the sum of my forces, which is FA plus negative FG. So this is where decisions come into play. You add up your forces. You are always, F net means add up your forces. Now, remember I told you all that I chose to make FG positive. Why? Because later on, I knew I was going to add a negative. So, you have a couple choices here. You could have written this as a negative FG, but don't count the negatives twice. So, if you choose to make FG negative, then you should just add up your forces. If you subtract a negative, you have made it a positive. Don't do both. Do not both make it negative when you're writing your givens, but also add a negative later on. Otherwise, you've canceled. Now they're adding together. I'll show you what happens if you do that. If you put this as a negative here, it would end up being 25 plus negative 19.6. You are saying that a negative and a negative cancel, make a positive. You're saying these forces add. Our picture clearly shows that they're in opposite directions. So just decide, you all, and be consistent. Either decide that your force is going to be negative, and you'll just plug it in as negative, or when you write your equation, use the vector to decide that it's negative. Whatever is less like, at the end of the day, just make certain these forces aren't helping each other. If one's up and one's down, they shouldn't be getting you a bigger number. They should be canceling out. That's the key. Whatever you do to make that happen, do that. So we'll see that as we plug them in. So F net equals 25 plus negative 19.6. You can see here they are not making a bigger number. One's up, one's down. They should cancel. Remember, your math should always make sense. It's physics. It's not just a math class. And it ends up being 25 minus 19.6, whatever. I like to put the add just so that we get used to the idea that it's adding. So that's my net force. It's positive. That matters. That means it's going up. A positive force after doing this addition means it's going up. So when we solve for acceleration here, so when we take F net equals ma and put that right over here, 5.4 equals 2 times a. Simple division, a equals 2.083. Positive. That positive matters. That positive says it's going up. So, yeah, did I? Oh, oops. I don't know why I did 2. I mixed them up. I did. Thank you. 5.4 divided by 2 is 2.7. There you go. Good catch. All right, and we look at that and say, does that make sense? Yeah, 2.7 is not bad. That's a fourth of what gravity is. That's okay. Again, if you're getting accelerations like 20 meters per second squared, that's getting high. It's 2 G's. Okay, so this is the process, y'all. This is kind of a simple example. This is kind of the simplest example we could have for this. 2 forces, add them up, find the net force, divide by mass to get acceleration. But every problem we're going to do is just variations of this. That's really all it boils down to. Draw your free body diagram, find the forces, add them up, divide by mass to get acceleration. You may do it in X and Y. be so much fun. Yeah.
Is it okay to just, I just took the first course
Mm-hmm.
and divided it by mass to get the acceleration and then subtracted not from it. Does that work too?
It's a good question. Let's just try it real quick. I don't think it's gonna work. Did it work?
Yeah, I understand that.
Okay. The thing you get into there is the process. There's a little hand with it's a tad tricky to kind of follow what you're doing. I recommend going through this process just because it's more. If you follow this recipe, you'll always get the right answer. That one gets a little hard to kind of justify how it works out. It works, I guess, but it's a little tricky to justify. That would be my concern with it. It's good to get in the habit of going through these steps for this, because if you're in the X direction, that won't work, for example. Yeah. If that works for you and you're confident in only applying it to the Y, go for it. At the end of the day, do what works. It's physics, if you get the right answer, you're doing something right. But yeah, it's a good question. All right, so great. Force of gravity, great problem. Really simple, but it outlines the process. So it's a really good one to look over and make sure you understand what I did, because if you do not understand this example, it only gets more complicated from here. So, all right. Next force, so we talked about gravity. We did an example with that. Normal force was the thing that's holding you all up. Normal force, if something is sitting on something, the normal force is the thing keeping it from falling. Or at least keeping it from falling as fast, or it could be the thing pushing it upwards. If you have something resting on top of a surface, there is a normal force. Something resting on top of something. Now, so F lowercase n, we'll do lowercase n just because, and I honestly do F capital N, but it just helps us not to get it confused with F net. Sometimes people use F capital N for net. You're going to notice in every problem, I'm going to write the word net because I think it's a safer bet. But some people will write F net as F capital N. So we'll use lowercase n for normal force, just for your all's future, whatever class you may have. Again, I will always write F net. I just think that's safer. But that's that. Okay, there is no equation for F net. So F gravity, mg. Always mg. F net, the normal force is a little funky. In general, how do you figure out the normal force? You have to know the acceleration in the y direction. You have to know whether or not the object is accelerating up or down. Now, I'll straight up tell you, for most problems, that's going to be really obvious. And most problems, for example, the stack of cards here on the table, it is not accelerating in the y direction. It is not flying upwards at a faster speed. It is not falling downwards at a faster speed. So really, that's the question you have to ask yourself. Is my object accelerating upwards, or is it accelerating downwards? If not, and it's resting on a surface, then Fn, the normal force, equals the force of gravity. And that will be true of a lot of your problems, but not all of them. A very easy example that disproves this is on an elevator. On an elevator, when you first get into an elevator, sure, the normal force equals the force of gravity. But the whole point of an elevator is it moves you up or down. Meaning, you're not moving, and then it starts moving you. That means there's an acceleration up or down, depending on whichever way that may be. If the elevator goes down, you have an acceleration downwards, because it's moving downwards. You went from not moving to moving in the negative downwards direction. If it's moving upwards, you're experiencing an acceleration upwards. That is physically what's moving you upwards. You're not moving, and now you're moving upwards. You had to accelerate. So an elevator is a classic problem for this, and I'm fairly certain there's one in the problem set to kind of go through. This normal force is always pointed the opposite direction of gravity. No. This normal force is always pointed away from the surface. That's an important clarification. Easy example where it's not the direction of gravity, a ramp. Gravity points that way. Normal force points that way. If you're like, ooh, I don't like that. Yeah, we're going to have to solve those problems. Yeah.
So if the elevator is going down, but slower than the acceleration of gravity, does that mean the normal force is greater than FG?
Yeah, so the question was if you're going down, but the acceleration is...
Just, like, it's not like the speed of gravity, it's like...
Yeah, so that's what gets tricky with an elevator. The normal force is only different than an elevator when it's accelerating. So actually it's just when an elevator is starting and just when it's ending. When that elevator is moving at a constant velocity, the net force is 0. So the force normal is actually equal to the force of gravity when it's moving at a constant velocity. That's one of those that's going to throw a lot of people off because they're like, but I'm going upwards at a constant velocity, which means you are not accelerating. Just because you're moving doesn't mean you're accelerating. That's an important kind of mantra to have in your head. Just because you're moving doesn't mean you're accelerating. Acceleration is increasing velocity, decreasing velocity, or changing direction of motion. So yeah, good question on that. Yeah, so it depends kind of where you're at. So there you go, yeah. When an elevator starts or stops, when you hit the bottom of a hill or when you reach the top of a hill. So you all have experienced this in a roller coaster. When you hit the bottom, or in your car, when you hit the bottom of the hill, you feel yourself like get pushed down into your seat. Gravity did not pull you down anymore. You are not getting pulled by gravity anymore when you hit the bottom of the hill. Your seat is literally accelerating you upwards because you were going down. So when you're going down a hill, you were going downwards. The normal force has to push you up. Otherwise, you should plow right into that ground. I mean, you would keep going downwards then. So when you all hit the bottom of a hill and your seat's pushing into you more, when you feel like you're pushing into it more, yeah, that's because the normal force is pushing back on you more to account for that you're no longer going down. How do you stop going down? You accelerate up. What's doing that? The normal force. So in the case here, force of gravity, force normal. The force normal is bigger than the force of gravity at the bottom. At the top, force gravity is actually bigger than force normal. You kind of fly a bit upwards, a bit. It's kind of funky. So, all right. So I'll leave that for a couple more seconds. And the next question, so I mentioned jumping as well. Jumping is a great example. Jumping, I push down on the floor. The only way for me to leave the floor is I got to beat gravity. Which means something has to push me more than gravity is pulling me down. So when you leave the ground, my question to y'all, 100-kilogram person wants to jump. What does the normal force need to be for that person to leave the ground, aka accelerate upwards? If they stay on the ground, their velocity hasn't changed. I went from 0 velocity to 0 velocity. If you kind of look at my whole body. Yeah, technically my shoulders did some things, but we're gonna look at the whole body. My center of mass. So, is it greater than 100 kilograms, greater than 980 newtons, less than 980 newtons, or 0 newtons? What does the normal force need to be to get me off the ground, to get me to accelerate upwards? All right, we'll go to 110. Five, four, three, two, one. If we want, so here's our person. If FG is down, if Fn is the same as Fg, you will not accelerate. If I want to go upwards, if I want to accelerate upwards, this needs to be bigger than Fn. So Fn needs to be bigger than Fg for this to happen. So now we just got to figure out what Fg is. That's m times g. Oh, what's m? 100 times 9.8. Yeah, we got to be bigger than 980 newtons. That is the requirement for you to leave that ground. If you are not pushing more than, if the ground does not push you more than that, you're not going upwards. It's not happening. There you go. Fantastic. So that gets the idea across. All right. Last force we're going to talk about today, and if we have some time, we'll be able to set up a problem with it. Tension. This is literally just any rope, any string, like it's always like a rope, a cable. any rope or cable, so like a chandelier hanging from a cable, tension in the wire. A tug of war, I guess you'd call it tension. If there is a rope, thread, cable, and it is pulling something, or the other thing is pulling it. For example, if you have something hanging from a ceiling, why isn't it falling? Tension is pushing up, gravity is pulling down. They cancel each other out. So yeah, if you got something hanging from a ceiling, you know, some chandelier, there it is. The tension will be exactly equal to gravity to cancel it out. If it's not, one of them's winning. If tension is bigger than force due to gravity, that means that wire is literally yanking the chandelier up into the ceiling. That's not happening. If Fg is bigger than the tension, that thing's accelerating downwards. Remember, everything comes down to acceleration. Anytime we're talking about forces and trying to understand the relationships, it all comes down to, is it accelerating? Is its velocity changing? If it is not changing, the net force is zero. All right, so again, calculate from Newton's second law. It is pointed away from it is pointed away from the object in the direction of the string. So this last one's kind of weird. Pointed away from force pulling on string. So in this case, gravity's pulling it down, tension is up. It's the direction the string's pulling it. Whatever way that may be. Tension here is not down, because that would mean that it is pulling the object down, at which point it would accelerate downward. Again, think through the logic there. Yeah?
And if you pulled on the chandelier, the tension would equal out.
Yep. Yeah, if I pulled down on this, if I applied a force downwards, tension would increase to counteract that. The second that cable cannot handle that tension, it snaps and everything falls. So whenever your downwards force beats whatever that rope's tension can be, because this tension can be any value as long as that rope holds. Yeah, but if I exceed what the rope can hold, there's a limit to what a rope can handle, it's going to snap. Yeah, so it's a great question. This tension value depends upon how much it's pulling, and we're assuming that rope's not going to snap on us. All right. Again, more of the same. Really just simple things to see if it's all making sense. A 20-kilogram chandelier hangs from the ceiling. What is the tension in the wire holding up the chandelier? If you're feeling like these are repetitive, yeah, in some ways they are. But really just getting the free body diagrams. How do you figure out these things? Because these are the skills, these simple skills we're doing in the clicker questions. This is what you have to do in the longer problems too. All right, we'll go to 1 minute on this. No reason to go much longer. Yeah.
Would we have to know if it's accelerating or not?
We're going to assume the chandelier is not. Yeah. So there, you do have to, when you're thinking about these problems, just think about what kind of makes it. Yeah, this chandelier, we're going to assume it's hanging and not, yeah. It is just, if something is just hanging from it, we're assuming it's not swinging left, right, or going up, down, unless otherwise stated. All right, we'll close this one out in 5, 4, 3, 2, 1. But yeah, it's a very important assumption, and you have to make assumptions in problems, y'all. I will try to clarify things as much as possible, but in this case, yeah, we do have to assume that that chandelier is just chilling. We have to assume that that chandelier is not crashing to the floor or flying upwards. And it may seem silly, but that is important. That is a decision that whether you make it explicitly or implicitly, you have to make. Is this thing flying upwards or downwards? You have to decide that for any problem I give you. So in this case, we draw, there's our chandelier. There's a wire here. Free body diagram, tension's up. Fg is down. We kind of already drew that. The acceleration is 0. So therefore, my F net is 0. Therefore, tension plus negative Fg equals 0. This seems silly that I'm writing all this, but this is the math that explains the logic. And there is some problems where you have to do that. So therefore the tension is Fg. That's the math that basically you all kind of did conceptually. M times G is going to be 196. You all did that, fantastic. But this is what you're going to end up writing out when solving problems. This one seems really simple. You didn't probably have to write it out. But this one, we're going to have to write that out. So we'll get to that in just a second. So yeah, how do you solve these problems? First step, all caps, draw a free body diagram. Critical. You have to draw, I would say have to. Try it without it. Have a great time. I don't recommend it. There's a reason we do it. It's not because we like extra work. It's because it makes the problem easier for us. It's because it makes it easier to organize the information. Anytime I tell you all a recommendation for a step to do, it's not because I want to give you more work. It's because it just will make it more likely for you to get the right answer. F net equals MA. We have to do the X and the Y direction separately. You have to do that. If the object, you have to decide if the object is not moving or if it's moving at a constant velocity. That's a very important distinction. A lot of people are cool with the acceleration being 0 when it's not moving. You also got to be cool with the acceleration being 0 if it's moving at a constant velocity. You have to remember that acceleration and velocity are two separate things. It sounds like I'm beating on the, like, if I've been being repetitive on this, it's because it's one of those really hard concepts. Like, it's one of those things that we get mixed up in our head that a lot of people do. It's a really common thing to do. So the more I say it, hopefully the less it happens. I would rather you all be annoyed at me repeating it so often than make the mistake. So, if it is going at a constant velocity, when you are in your car going 60 miles per hour with cruise control on, your acceleration is 0. You are moving, but you're not accelerating. When you all are going up in an elevator at a constant velocity, the acceleration is 0. You're moving, the acceleration is 0. All right. And if multiple objects move together, it is a great idea to consider them together. We're going to do it. You're like, what does that mean? Like, what does that look like? This problem is the one I'm referring to, and we'll solve through this one next time. These problems are coupled together by a string, meaning whatever happens to one object happens to the other. This object gets pulled down, this string effectively couples them together, so whatever one does, the other does. When this one gets pulled down, this one also gets pulled. What does that mean? That means they both have the same acceleration. And that's going to be, there's a couple ways to solve this problem, and that's one of the ways to do it. Yeah, they will both experience the same acceleration. So, real quick, we got a couple minutes. Again, we have so little time in this class, and I got to kind of milk every minute I can. Find the tension on each of the 3 cables supporting the traffic light if it weighs 200 newtons. So, what a blessing. I gave you the force due to gravity. Don't even have to do M times G. Oh, man, I know you were nervous about that. Draw a free body diagram, y'all. That's the first step. Here's my traffic light. See if we can get the free body diagram. That's all we'll kind of do here. We'll do that and talk about it. We have a tension 1 going up at a 41 degree, tension 2 going up at a 63 degree. Those combine to make tension 3. What you have to recognize to draw the free body diagram is what's actually touching my lamp. This wire here, tension 1, not touching it. Tension 2, it's not touching it either. So when you draw this free body diagram, we got the force of gravity, the weight going down, and we have tension 3 pulling up. Great, that'll give us tension 3. That's not what it's asking for us to solve for. What we're going to have to do next class is we're going to have to recognize that you then take this, and now we have to look at this part. Great, tension 3 is downwards. Well, tension 3, we then kind of draw another box. At this spot, tension 3 pulls downwards, tension 2 pulls this way, and tension 1 pulls this way. So we have the pleasure of drawing 2 free body diagrams here. Think about that. See if you can wrestle through that. Try to understand that. If you can't draw these, like if we're not able to draw these pictures, the rest of the problem you won't be able to do. That's how important this step is. So look through this, think through this, see if you are okay with that. If not, wrestle with it, because you have to be able to draw these pictures to be able to solve this problem. All right, y'all, good luck to you. Remember, you got to look like a day or 2 more for the 2D kinematics. But yeah, start wrestling with this, these problems if possible, y'all.
clicker, it didn't sign me out.